solution for commercial shipping. At that time, fuel was running out, price of fuel was going up, and there was a real threat to commercial shipping. So this was a pretty well-funded research project. They did a huge amount of testing, wind tunnel testing at the time, and got a lot of credibility. Unfortunately, it didn't come to fruition. The fuel price dropped, and it lay there for many, many years until a Silicon Valley entrepreneur called Tom Perkins, founder of venture capital probably. He's probably responsible for more technology development coming out of the US than any other single person in recent times. And he asked Jerry Dykstra, a naval architect, if he could come up with a radical, nice solution for his new big boat, which he wanted to get rid of crew. Yeah, he didn't want to have a lot of crew. He wanted a boat that could have a sailing system that could be handled by one or two people. He also, being a true venture capitalist, of course, asked several people at the same time that and studied them all. And in his own words, he said he studied them long and hard for fully 30 seconds, and then he decided on the DynaRig as the way forward. So that's the background to it. So what is it exactly? So the DynaRig is effectively like a bat wing, I guess, in some ways. It's a mast, and it's an unsupported mast. This is the variant that we introduced when we first did it. It's an unsupported mast, so it's freestanding. It comprises of a set of yards which run transversely across the mast, separated from trusses, and the sails furl into cavities within the mast. When they come out of the mast, the sail runs along the top yard and the bottom yard. So in such a way that when all the sails are set, it creates a continuous wing. So very unlike the old square riggers where there were gaps all the way down. It creates one single wing, like an aircraft wing as such. Then the beauty of it is that it lends itself to full automation in this process. So what does it do for us which other sailing boats don't really do? Well, basically, ease of handling is the first point. It's very much simple push-button operation. One person can control it. Actually, all sails can be set in 6 minutes on the big boats that were out there, and you can tack and maneuver the boat. I'm a sailor, I love sailing, and I often tell people it's like sailing a laser. You know, you're in control of the boat. Yeah, you don't need to rely on lots of crew. Another really significant point is it's safe. You know, and what a lot of people don't realize is that sails are normally attached to the hull, and they're attached to the hull somehow or other by ropes or wires or sheets. And those ropes and wires and sheets are putting the driving force into the hull. So there's a lot of load on those things. And they have to be adjusted all the time. Not the case in the DynaRig. Everything happens above your head. Everything, you know, there's no ropes on the deck at all. So crew can walk around, guests on super yachts can walk around, everyone can walk around and actually ignore the fact that there's not anything going on above the deck. So in that context, inherently safe. A really important point for commercial vessels as well, because there's a lot of stuff lying around on decks and ropes sliding across decks with high loads in them, and not a nice thing to be caught around any sort of structure that's out there. And a third point, obviously, is what we're here today. I mean, in old terminology, it's very green. You know, the wind is out there, it is free. Everyone's said it's actually pretty green way to use it. Of course, nothing's totally green. There are non-green materials in there, but it actually is a free mechanism of propulsion. Today, we've heard a lot of things out there, and a lot of things are very novel, yeah, and need development and so on. And some of them are great, and some things have already been developed. I'm an engineer. I've been responsible for the development of quite a few novel things in my life. I'm mainly in composites, and I do know how difficult it is. You know, I mean, it's easy somehow to be put down in a little area. We say, well, they can build that and design it, but actually the devil is in the detail in these things, and getting these things to work properly does need a huge amount of engineering resource. So today there are two very large vessels out there, and they have between them over 20 years of seagoing experience. in all range of conditions. Both the big vessels have been exposed to severe storm conditions, 60 knots plus, and sailed through those. How they got themselves into that condition, always a bit of a worry to me, you know, with the modern forecasting that's out there, but nevertheless they have. More importantly, the sail setting automated process is so easy that they do it all the time. Press a button, set the sail, press another button, it comes in. More than 10,000 different sail sets in the course of that set of time. And the first boat we did, now 14 years old, the rigs have never been out. No single item of hardware has been taken off the rig until last year, when we had the first opportunity to do any maintenance on that at all as such. Another key aspect to this is another little technology I was pioneered and developed a few years ago, was the use of embedded fiber optic strain monitoring technology, using a concept known as a fiber brag grating. We can talk about that separately. But what it means is we have a network of fiber optic cables embedded into the composite structure, giving us real-time live load data, live accurate strain data all the time. It's used on board to show them what they're doing in terms of warnings. It's used to give them driving forces and heeling forces. It also comes back to us every morning at 3 o'clock. So I see exactly what all the big vessels have done the night before, and we monitor the lifetime history of these structures. So we can go to the insurance company and say, we don't need to take these rigs out after 10 years like they do on all the other big boats, because here's the record every single second of every day since we first lifted that rig and put it into the boat. It's quite low tech. The sails are throwback to actually low tech material, so very, very cheap sails, the cheapest part of the boat, because each sail is very lightly loaded. The load of the vessel, in this case, spread over 15 sails, and it's held at the top and held at the bottom. The sail's not highly loaded, and there's nothing for them to chafe on, you know. And because they're tight, they don't flog like the old square riggers in light airs, where a lot of damage was done. Basically, it's proven itself in terms of reliability and maintenance over the last few years. Here you see extensive interest right now. I have another couple of big projects, bigger than these, running at the moment. So you can see, actually, I think we're well north of 105 meters on the next one. The two that are out there, Maltese Falcon at 90, and Black Pearl at 106 meters. So a number of naval architects very keen to promote that, and a number of yards as well. So it's out there. It's proven technology, but it is on a super yacht, guys, and everyone associates super yacht with a lot of money and so on. And so how can we move that back into where it came from, the commercialization? And basically, the key aspects to commercialize the rig, most of them are there. The performance knowledge is there, the reliability is there, the operational experience is there. You know, now, effectively, we have another thing, real-time route planning, which I'll come on to a bit later, is there as well that can do it. What we don't have is a low enough cost, and cost is very important, as everyone sitting around here. So we've really got to commercialize the rig by addressing that CapEx problem. And the way we've done this, and I have a number of commercial projects running at the moment, including Danielle's, is to really step back and look at what's key to this. We don't need the aesthetics. We don't need the, you know, the beautiful paint finish better than a Ferrari. Yeah, I know there's a story there, but I'll tell you that later if anyone wants to come and talk to me. But the sort of things we're doing is looking at a different mast shape, a simpler mast shape. We're not going to furl the sail into the cavity of the mast. We're going to furl it outside the mast, which is a normal practice in a lot of race boats even still. And we're going to secure the yards to the mast by a steel framework structure. So this slashes the cost dramatically. The rigs themselves, the masts themselves, doesn't need to be the high sophisticated carbon fibre that we've used on the super yachts. We can use a lower grade of carbon fibre. We're less sensitive to weight in that. We can use glass fibres in there as well. We need to deal with the fatigue life. We could even perhaps use metals. In the yards, we will be using aluminium yards as well. So I better just, I see. So we, as I said, the project's pretty well developed right now. We're into detailed design phase on all these aspects. So I've just got 3 or 4 more minutes. I noticed the time is going on this. But this is, we've talked a lot about, you know, sail only as a hybrid vessel. I mean, clearly, it's going to be a hybrid vessel going forward. And then this is a study that was done by the Dykstra guys on a project which we nearly got, we didn't get, called the Ecoliner, where a key aspect to this was a vessel that could do the North Atlantic route, the circular route around the North Atlantic, which is a well-known traditional route. And what we really have today is much better weather prediction programs. So we have that, the vessels have that coming in updated every 2 or 3 hours. And using that information, you can properly plan the route of your vessel all the time, and that can be continuously planned. So there's a piece of software, a number of people have done it. The Dykstra guys have done a nice one, which you put in your scheduled arrival time, and it tells you what route to go. And it takes into account the speed of the vessel, what minimum speed you want to achieve, when you switch the engines on or not. And to give you an idea, here's the outcome of this, where a required speed of 12 knots was required. Now, this is real data from the last 20 years of wind tunnel data, given a fixed schedule of voyaging. So this is actually running the vessel through that historic data of the last 20 years. At 12 knots, we're getting around about 20% fuel consumption. Fuel consumption reduction, sorry. Fuel consumption is really clearly driven by how fast you want to average effectively. So the faster you want to go, the earlier you need to put the engines on if you run out of wind on these things. So clearly, if you drop the boat speed average that you want to achieve to 10 knots in this case, then the fuel consumption jumps down or drops down even further. So you can get 30–40% fuel savings. I mean, of course, if you've got enough time, you can sail all the way. And in fact, Black Pearl, the 106-metre boat out there we have at the moment, she's 3,200 tons. She has an electrical regeneration system. And so when she's sailing, she's generating her power on board through through her main propeller system. And that power runs all the hotel services and fills the battery bank, which gives them about 24 hours electric motoring capacity. So she's done many voyages, long voyages, without burning a single gram of fossil fuel as a result of that. Very easy to expand that to hydrogen-powered assistance or perhaps even more electric battery-powered systems. Several commercial variants out there which we're discussing today. Some of these were in advanced engineering analysis. By that I mean we've been working on them for a few months, doing the full detailed drawings. You can see Danielle's picture in the top right, thank you, which is a very beautiful looking boat, and again specifically designed vessel for sailing performance as well. It's a 3-masted vessel. See the Ecoliner. On the left is a French project which we're working with from a guy called Yvan Boignon, who is determined also to sweep plastic out of the seas. He's been using this. He's been working on this for a number of years. He's 2 or 3 years. He's got a variant of the DynaRig on there, and it seems to be moving forward pretty well. This project, we've done a lot of work on it. So just to summarize, reliable, proven technology, really working on the commercialization of all of this now. It could be 100% sailing capability, more likely to be a hybrid version. Where are we in terms of target price? Probably 2 to 3 million euros a rig, on the basis of limited numbers, i.e. the projects we're doing at the moment. And like many people have said today already, the key to getting the price down is volume. You know, if we could apply the same per ton rate that the Far East are building in today, it would be a fraction of that price even. So that's it. I just threw in a little pointer here. I said at the end, maybe that's a rebellious Nobel Prize winner for literature did get it right. I think you'll all probably know who I'm referring to. The answer, my friend, is blowing in the wind.
Thank you, Damon. Okay, so now we are going to go to Stéphanie Lesage, but she's going to speak to us, but that she's got a short video that she wants to share first, which hopefully Nigel and team will get
Today, we are facing an emergency, a climate emergency. From aerospace to shipping, we transfer our knowledge to bring you a groundbreaking solution. Using wind, powerful, renewable, abundant, and free. We harness its power to reduce CO2 emissions by 20%. Operated from the bridge, no deck intervention is needed. It's a simple push-button system with integrated eco-routing, respecting ETA and maximizing savings. A user-friendly interface to facilitate the operation of the product. Seawing, a revolutionary wind propulsion technology. 1,000 square meters of flying wing. 100% automated, operated by the push of a button. Using cutting-edge digital twin technology, we maximize the power through flight control. Flying as an aircraft, its position is recalculated every 300 milliseconds. We maximize the use through our integrated eco-routing software to take advantage of the most favorable meteorological systems. Simple to operate, 100% automated, powerful, using dynamic flight and flying over 200 meters. Wind, taking advantage of free energy. Harnessing the power of wind is our motto. Make a difference. Come fly with us.
Hi, Stéphanie. We can.
Hello, everybody.
Yeah, we can see you well.
Yeah.
I hear you well.
Okay, great. So I will share my screen right away. So let me know if it's okay for you and if you can see it.
Looks good.
It's okay? Okay, great. So hello, everybody, and thank you very much for the invitation. Thank you to Maida and his team for the organization of this event. I'm very pleased to be with you and apologize for not being, for not attending physically, but I'm with you. So I will present Airseas and its product, the Seawing. So first of all, the company, who we are. So Airseas was founded in 2016 by a former engineer who want to transfer his aeronautical expertise to the maritime sector. So we are based in France and located in Nantes. We recently moved this summer. So our great, I would say, strength is our team. A team composed of many profiles coming from different sectors, from the maritime sector, but also from the aeronautical sector and from the renewable energy sector. All in all, we are now 90 employees. So let's have a look at the product now, the Seawing. So the main features of the Seawing. So the Seawing is flying really high, between 200 meters and 300 meters in the sky to capture a more constant and powerful wind. The Seawing has a dynamic flight to be more and multiply its performance, and it's fully automated. So let's have a look in detail of how it works. So it's an integrated solution, and it's composed of a hardware part with 1,000 square meter kites, controlled automatically by a pod, and the pod integrates the flight control laws from the aeronautical sector. We have also a deck machinery ensuring automatic folding, unfolding, and storage of the wing. And we have also integrated through the pod and through our eco-routing solution, the digital twin technology. The eco-routing solution will combine and consolidate the ocean weather data, the ship data, and the wing data, and to propose the optimized route to the captain, optimized route in terms of fuel consumption and performance of the wing. So all in all, we are able to maximize the use of the wing and the performance of the wing. And we can achieve on average 20% of fuel reduction and associated emission. So our value proposition is it's a disruptive technology, definitely. To decarbonize the shipping sector, we need to innovate, and that's what we're doing at Airseas. So our solution is really simple. It's a push button solution. So it does not require any intervention from the crew. It's simple to retrofit and to swap from a ship to another, and it can be installed on any type of ship. As I mentioned, it's cost cutting, 20% on average, and it can be up to 40% on transoceanic routes. And all in all, it will allow ship owners to meet the environmental objectives. So as it was said this morning, definitely ship owners are currently identifying what are the available solutions on the market. And we have customer and prospect coming and knocking at the door to see what is behind the Seawing. So we have 2 launch customers, Airbus with the ship owner Louis Dreyfus Armateur for 1 Seawing, and K-Line, the Japanese ship owner, with 2 Seawing and 49 options. So our system has received the approval in principle by Bureau Veritas, the French Class Society, and the Japanese one, Class NK. So a couple of messages we want to convey today. That's the Seawing and wind propulsion is available right now to reduce the fuel consumption and to start to decarbonize the shipping sector immediately. And we need it. We need to drop today emissions because the damage done by carbon emission produced from now will not be reversed by any kind of solution or technology. So shipping can, we really are convinced at Airseas that shipping can win the race of zero carbon. But we need to invest and to apply now renewable propulsion technologies, which can be combined with alternative fuel today and in the long term. So for us, there is a huge opportunity for the maritime sector to save time and money. And for us, it's really time to seize it. Thank you for your attention.
Thank you, Stéphanie. So then, yeah, finally, Frank seamlessly appears before us. We can see you, Frank. Can we hear you?
Very good.
Yes.
Very good to have me here. I'm sorry that I didn't manage to get to Glasgow this morning. Now I'm in the comfort of my house again, and that's good. Let me start my presentation for today. I'm the CEO and the founder of Econowind, and I also want to speak a little bit about the contribution of wind into shipping. If you look at ship owners, they have a growing pain. the ship owners' challenge really is obviously with the rest of the world to cut carbon intensity. But the general rule is that they have to do that by 2% annually. And most of the ships going out there today, they will fulfill the need of maybe 1 or 2 years ago, but they're really feeling that they have to start getting down a few percent every year. In the European Union, the ETS will add the cost further. And that is when you look at wind or any investment, most ship owners are comparing still to the price of diesel, whatever they do. And they don't compare yet to the price of the higher prices probably will be there in the future by more modern, more futuristic and sustainable fuels. Still, the IMO sets the target to go down at 70%, but the basic is it's an ongoing process, and really what they need to do is to start today, like Stéphanie was also saying. It is possible to start today, and the new fuels, it's good to talk about, it's good to investigate, but everybody knows the infrastructure needed for there is not going to be there the first years. So the IMO expectations from a little bit, previously, they had all kinds of ideas what could be together the thing, and the wind was in the beginning not in there. But if you come to look at it in the real sustainable future, we really are going to take energy from the wind and the sun, but let's focus here on the wind. Put it in a windmill, and then we make hydrogen or whatever, but at least the energy to convert that into synthetic fuels. And by now, already 70% of the energy that was in the wind is lost due to all these transformations. Then we transport it and put it in a combustion engine. And in the end, the combustion engine only has an efficiency of some 60% around. So again, 45% is lost. And same with the propeller. So in the end, 90% of the power that was in the wind is lost due to all these transformation. And then when you look at a wind-assisted ship, where you take the energy out of the wind and put it into driving force right away, whenever you see a system of a limited size, you can multiply it by 8 in your vision, because that's what it does if you compare it to the future. But still, not always good winds, everybody knows that. And when we want to arrive in time, it is good to have hybrid systems, also like the previous speakers have said. Another thing is that the wind basically is free. So if you compare all the costs, euro per kilowatt hour, on the bottom is wind, very small, but it says zero cost. Unfortunately, we do need the installations, and also that was said, installations can be quite expensive. But the good news is the leasing cost and the savings, they are coming closer together. And depending on the routing and the systems, of course, and the installations, savings are going up and costs are coming down. And we're getting to that point, what we call the singularity point, where the leasing cost actually is lower or first equals the savings. So on the financial side, there's no reason. We are still looking at compared to diesel. So with our solutions, we do have a financial goal that is quite lower than other things that are being said, because we mean this really against the current diesel. Then there is a basic 2 approaches, because here in Ship Zero, obviously we're trying to go to total zero emission. But you know, how do you reach that? And there's 2 principal ways. You start at zero emission and scale up the ships, or you start at the current ships and you scale up the savings, the reductions. So how does that look? Obviously, the first approach is to start in a ship that is fully emission-free. You scale them up bigger and more, and then you multiply by 20,000 ships that are out there today. So everybody can feel in their water that that is not going to be an easy task. It's going to take a long time. The other approach is to start with the current ships, let them go around, but try to add wind-assisted propulsion to them which most of the wind suppliers are doing. And in the end, we scale up the units. And that is easy to do, much easier to do in an industrial way. But in the end, these two approaches will meet sometime in the future. In the meantime, we can start saving today. At this moment, if you look at the total offering as said by the IWSA, many wind assist ships are available today. There's different suppliers doing all kinds of technologies, but everybody is approximately on the same page. Wind is possible to take today. We, from our side, we started this project by Conoship, the Technical University of Delft and Marin around 2011 to study wind propulsion generally. And the end conclusion was that wind-assisted propulsion is very feasible. But the second conclusion was that as you're doing it on current ships, there's lots of things that you have to take into consideration. And so the idea was start systems that can do up to some 25% fuel reduction. It's the same numbers we hear because it doesn't influence with the operations of the ship as much as reduced as much as possible. And we really like to start with a small percentage, but then multiply it as fast as we can. Anyway, from that study, it turned out that the suction sail, which was tested in the around 85 by Jacques Cousteau, is the most promising for the total line of demands that were set for a normal commercial shipping. And that's what we worked on. It's the suction sail concept. We did make it foldable, and we made it appear in a fixed flat rack and a containerized version. So I will go through the technology quickly and how it looks. In the containerized version, it looks like this. It's a big 40-foot container, and two airplane-like wings flap out of the container. It doesn't look like they fit, but that's due to the photograph. I can tell you, within 1.5 minutes, the wings are inside the container and folded away. The second version is a flat rack version, which is possible to move by the hatch crane. The disadvantage of the container was that the ship was able to unload it, but this one was not allowed to unload it in the harbor. It had to be done by the harbor crane with quite some extra cost. So this solution is the same wings. They fold down quickly, but then they can be set to the first of the last hatch, or in this ship, the Frisian Sea, even right behind it. So it doesn't interfere with the hatches at all. Or like the versions of Jan van Dam, the Anki, it's done welded onto the front of the ship, onto the bow, a retrofit, and it doesn't have to be moved. It can fall down forward or backward, so they still can enter into enclosed loading docks. And why a suction sail? Well, the suction itself has an influence on the aerodynamics of the wind around the wing. And this really increases the force a lot. This is maximizing airplane dynamics. And it works like this. The wind comes around the wing. Obviously here on the back side is the high pressure side, and around to the front, what you see here is the low pressure side. And the low pressure really sucks the wing forward, and it gives a thrust force. But normally, if you do not have the suction, and this is a low pressure area just behind the thickest part of the wing, the airflow is not really nice and good. So the nice thing of this is that once we turn off the ventilator, we can, with the power of the ventilator, we can regulate the thrust force. So because a wing without a suction, it's quite a little different. The airflow around the wing is wobbling more, and the pressures are not as low, and therefore the thrust force is low. So really shutting down the wind in case needed is a matter of switching the ventilator off, which is reacting very fast. And a little bit on the theory of wind propulsion generally. In a normal situation on a ship, the propeller thrust is equal to the resistance of the water and the wind, and thus with a certain setting of the motor, there is an equilibrium at a certain speed. When you add wind power in any way, whichever way you do that, what happens is there is an extra force, and so the speed will increase, increasing the resistance of the water and the resistance through the wind. And then it's possible, of course, to reduce the propeller thrust, keep the same speed with less propeller thrust. But in the reality, that's not how it works. In the reality, the speed increases, and that is part of the saving. So obviously the maximum saving is at the original speed, but if you go a little faster, when you're asked to slow down anyway, that is definitely an option that the captain will take. But the end conclusion is that we always need to evaluate extra speed and fuel consumptions together in order to evaluate the real savings. So we did some testing, and it was pushed by the Interreg WASP project by the North Sea region. The 3 ships were allowed to be installed, and two other ships with other systems. And all of these are being followed over the past 2 years and the coming year, and see what really happens when you do it in reality. So the Yankee was tested, and before we started, we made a prediction. And you see here that when a wind power of some 10 meters per second at the 90 degrees angles, we estimated indeed some 25% savings. So then we went really sailing, and we really found the influence on the ship speed, not so much on the actual on the actual savings at the moment, but at the general savings over time. And how does that work? Well, when you have a certain wind statistics at a certain spot with 0 speed, you see, we took one spot anywhere on the ocean, and then we calculated what happens when the ship starts moving. And what you see that most of the time, the ship has headwind. This is obviously due to his own speed. And the faster it goes, the harder the headwind, and the lesser wind comes from the side. And then when you take into consideration the amount of the angle in front, which most systems can't take, so the higher you can go against the wind, the better it is. Because if you, there is a certain angle which wind you can't use, and therefore the systems always shut down or are taken down, and then you have to go on the engine. And obviously when you go across the ocean, like was said in the first presentation, you have a chance to find a wind all the time. But the most commercial ships, they just follow the routes that they take. Just a short video from some seconds to give you an idea what it looks like. The systems go automatically up and fold. And then a little bit of how it looks like when you have a wind power 7. And obviously, everybody thinks now that that is due to the wind propulsor, but in reality, that really is due to the waves. And the ship just is dancing on the waves. Well, looking a little bit at the measured results, as I said before, it is obviously when you have the good wind, when you have the most influence. And here we see the foils in the blue at the bottom. You see the time in a certain test situation. We have done hundreds of these tests. But of course, this one was calculated nice, and this was at the 90 degree, 15 meters per second. So this was approximately what we anticipated ahead of time. And you see that if the foils were up for about an hour, they were put up in the beginning. And at that moment, the ship was going 8.9 knots through the water. The wind was around 14 to 15 knots, and the fuel consumption was 21.3 kilogram per whatever. But that's the FOC. And then what you see that the ship indeed, due to the extra force, was speeding up. So the throttle was exactly the same. The only thing that changed was that the foil went up and the foil went down again. So after some 20 minutes, the speed was going up to 10.1 knots. And at the same time, the propeller is going through the water easier. And as the RPM of the motor is controlled to be the same, the torque gets less, so the injection goes less, all automated, and the fuel consumption went down to 18.7. And when the foil went down, you saw the opposite going again. The ship slowed down to 9.1. We didn't do it long enough in this particular thing. And by that time, the wind has gone down a little bit. After putting up the foil again, the fuel consumption went back up to 21.3. And after putting up the system again for the last half hour, you see the same effects again. So the results, that is with the statistics I was mentioning ahead of time, the real question is, what is the reality over a whole year and in overall routes? And obviously, as I said, this is being measured over a period of time by the DynaRig funded program, WASP. They will, in the end, publish all this, but what we do see is that the guys that wanted to do this quickest were a few people that are going through the Baltic and a lot of times through the Kiel Canal and small stretches. They go in and out of harbors. The statistics are really not really favorable, but once they go out there and once they put up the sails, they function as expected. So the takeaway message for you all today and for all the ship owners around, wind assist is available today. And the nice thing, wind is available today. So there's really no reason, especially since the savings of systems are getting down, are getting up where the leasing costs go down, and the singularity points almost here. Together with some good financing schemes, it is possible. But furthermore, especially with the newer fuels that are great for the future and will be needed in shipping, it is good to realize that anybody who invests in wind assist shipping now is reducing the amount of fuel they need in 5 to 10 years when those become available. Thank you very much. And I think now we are open for questions in the next session.
Thank you, Frank.